Now with these different queues, okay, then we can also allow processes to move between the queues. Okay. So far we have talked about this. We have multiple levels of queues, right? and we do scheduling both within the queues and across the queues. Now there are reasons that why we also want the process to be able to move across queues. Okay. What that means is that a process can move from one queue to another, moving from say a foreground queue to a background queue. For example, a process may change its behavior, change its characteristics in terms of its CPU burst. A process that we believe that we consider iterative before now become non-iterative, right? And how do we know that? Right? We can detect it by observing the CPU burst. The interactive process, generally speaking, has short CPU bursts because they require interactivity. They wouldn't just use the CPU for a long time because they have to wait for the user to input or generate output for the user to respond to the output. Right? So interactive processes, they generally have short CPU bursts. But the background processes or batch processes, they typically have long CPU bursts because they do not require interactivity. Right? So once we start a background process, it can right? If it is given the CPU, it can use it for a long time. Right? So what that means is, in other words, it has long CPU bursts. So that is how we can determine when a process changes behavior, right? And that's when we should move a process. In the example I just gave you, from the foreground process queue to a background process queue. Right? We just observe how long is this process CPU burst. Okay. If a process uses too much CPU, then we move it to a background queue, right? or in general speaking, we move to a lower priority queue. Right? If we have multiple queues, like the example we saw before, right? we have 6 queues, right? Then we just move it to a lower priority queue. Right? That's the idea. So we can move a process from a higher priority queue, which is a generally more interactive process queue, to a lower priority queue, which is a generally less interactive process queue. Or we can also move a process from a lower priority queue to a higher priority queue in order to implement the aging which I just talked about. Right? Because remember that we also have to schedule across the queues, and if we always prioritize the queues with the higher priority, then the processes in the lower priority queues may get starved. So to implement aging, what we can do is one way to do it is to move a process. Right? Is to move a process from lower priority queue to a higher priority queue. So specifically, if a process has waited too long, right? So we can measure the amount of time that every process has been waiting to be scheduled. Right? If a process has been waiting too long, then we'll move it to a higher priority queue. Right? This is quite similar to the aging we talked about before when we were discussing priority scheduling. Right? In priority scheduling, remember that is a scheduler for a single ready queue. Then, in order to implement aging, we just gradually increase the priority of a process that has been waiting to be scheduled. So we increase the priority, right, in the priority scheduling. Now, in this case, when we have multiple level queues, what we need to do is we increase we move the process from a lower priority queue to a higher priority queue, right? So that in essence also increase this process's priority when we move it to a higher priority queue, right? I hope I've made it clear. Now, so this is just one way to implement to prevent starvation, right? And we talk about that the different ways, right? Let me go back to different ways to schedule cross processes. If we use fixed priority scheduling, then we need to implement aging, like we just saw, okay? By moving processes from lower priority queues to higher priority queues as they wait to be scheduled. But if we use time sharing across the queues, okay, then then we don't have this problem, right? Then we don't have a salvation problem, because every queue, no matter how low the priority is, the queue has, right? All the processes in that queue can still get scheduled, because we're doing time sharing across all the queues. Okay, just to make it clearer for you. Okay. So now let's look at an example, right? So by the way, right? So when we allow processes to move across queues, we call this kind of scheduling multi-level feedback queue scheduling. And the scheduling we talked about before, just now, is multi-level queue scheduling, because we have multiple queues for scheduling, right? And when we allow process to move across queues, we call it a feedback queue scheduling, because essentially we have a feedback loop here. Based on the scheduling decision, we decide where to place a queue, right? So that's the feedback here. Without feedback, right, when every process is just statically assigned to its queue, right? And then that's the multi-level queue scheduling we saw before. Right? There's no feedback, so the decision, right, the scheduling decision made by the scheduler does not affect the scheduling. Okay, that's what the feedback means. If the scheduling decision made by the scheduler in the end comes back and affect the next scheduling decision, then we say we have a feedback. Right? Does it make sense? Right? So we have a scheduler. Okay, so we have a scheduler here. Okay, so it is given a set of processes. Okay, and then it makes a scheduling decision. Right? This is scheduling decision. What the scheduling decision is, the scheduling decision is basically which process to schedule next, right? And with multiple queue, then it's more than that. So first we have decided which queue to schedule next, and then within the queue which process to schedule next, right? So this schedule I'm talking about here, right, is the multi-level queue scheduler. Okay, so includes the scheduling both within the queues and scheduling across the queues. Okay, it has two-level scheduling here. The scheduler I'm talking about here. Right, so if we only have this feed forward, right, we only have this one direction diagram, right, then that is the basic multi-level queue scheduling. Now, in multi-level feedback queue scheduling, what happens is that the scheduling decision that we make will come back and influence our scheduling. Okay, so for example, to implement aging, right, so aging. That's how we do it, aging, right? If a process has been waiting long enough, right, and that will come back, okay, and change the position of the process in the queue. Not change the position, but move the process from one queue to another, right? So that's how the decision affects the placement of the processes, okay, in the queues, and that will then affect the scheduling. Right, affect the scheduling and the next scheduling decision. Does that make sense? Right? So that's the scheduling decision comes back and influences the scheduling. So that's why we say we have a feedback loop. Here. Okay, that's basically what it means. Alright, so now let's look at a concrete example. So here we consider three queues. Okay, three queues. And we have Q0, Q1, Q2. In Q0 we use round robin scheduling with the time quantum of 8 milliseconds. Okay, and in Q1 we also use round robin scheduling with the time quantum of 16 milliseconds, and in Q2 we use first come first serve scheduling. Okay, now so based on this, so I'm telling you the scheduler that we are using and the parameters of the schedulers. Right? But based on this, you can give guys what kind of processes should go to which exact queue. So obviously Q2 is for background processes. Those are the processes that are executed in batch and does not require interactivity. And Q1, right, both Q0 and Q1 are for processes that require interactivity. But then the difference between Q2 and Q1 is that Q0 has a smaller time quantum, while Q1 has a bigger time quantum. So Q0 is for processes with require higher interactivity because the quantum is smaller. Right? when we make the quantum smaller, that will give a process a higher interactivity. Right, so the process wastes less amount of time to get scheduled again. Right? So it allows higher interactivity. And in Q1, then we give the processes a longer time quantum, so it is for the process that require less interactivity. Okay? So that's the basic idea. Now, right, so with the multi-level feedback queue scheduling, you see that we not only have multiple queues, right? So we have these queues here, okay? But we also have and these queues are connected, right? Essentially they're connected, right? So let me explain how they are connected. So across the queues, first of all, across the queues, so within each queue, we already know how to do scheduling. Right? In this example, right? Let me write them down. So this is Q0, and this is Q1, and this is Q2. Right? Q0 and Q1 use round robin. Q2 use first come first serve. Round robin, and first come first serve. Okay. And then across the queues, we give the highest priority to Q0. Okay. So Q0 is this is priority. Right? It goes from high to low. And this is priority, okay, from high to low. Okay, so give the process in Q0 the highest priority, and the process in Q1 lesser priority, and Q2 the lowest priority. Okay, that's what we do. Right? We assume we do fixed priority scheduling. Okay, across the queues. Now, but then we allow processes to move across queues, and so processes with so with a process, right? So we'll process that. So first of all, process with really short speed bursts, right? They will naturally fit in Q0, right? But as the process, when their CPU bursts grow, okay. Let's say when one process used to have a CPU burst that is this is at the same level of the 8 milliseconds, right? So this is millisecond at the time quantum, okay. And then that process is starting in Q0, but as that process increases the CPU burst because its behavior is changing, right? Then we will move that process from Q0 to Q1, right? And then when a process even further increases its CPU burst, right? That's when the process that is used to be interactive, right? Although its interactivity is at the level of 16 milliseconds, so that's why it is feed naturally in Q1. But later on, it also changes behavior. Now it does not require interactivity at all, right? And it becomes a batch process, a background process. In that case, what that means, it has a CPU burst that becomes much longer, okay, much longer than the 16 milliseconds of time quantum, right? And then that process will be moved, okay, to Q2. Okay, so that's the idea, right? So as the process changes behavior, okay, as the process changes behavior, it will move, okay, from the high interactivity queue to a low interactivity queue, and even to a non-interactive queue, okay, a background queue, a background process queue, right? And also as it moves from a high interactivity queue to a low interactivity queue, its priority also gets decreased. Okay, so that's the basic idea, right? And also, so you see that how the queues are connected, right? Of course, we can also have connections in the other way to implement aging, which is not shown in this example, right? So as a process, say a process that is sitting in the first come first serve queue that has been waited for long enough, right? And then we can move the process, okay, to a higher priority queue, right? This low interactivity queue, right? And even in that case, the process may also get starved, right? Because if we have so many high interactivity processes in Q0, then the process in Q1 can still get starved, right? So then what we do is that we also move a process. Well, a process that has waited long enough in Q1, we can also move it, okay, to Q0. Okay? So see, that's another way to connect the queues. Okay? But that's the basic idea of multi-level feedback queue scheduling. I see. So the two different reasons, at least there are two different reasons why we want to move process across the queues. Okay, from high priority to low priority, or from low priority to high priority. Okay? Both are important. All right. So so far everything we have talked about is, if you haven't noticed, is about a single uniprocessor scheduling. Okay. And all the algorithms we have talked so far, we assume there's only one processor. But as you know that, I also mentioned a few times in our class already that multiprocessing and multi-core are really important today. Okay, because that is how we can continue the growth performance growth of computers, right? And follow the Moore's law. Okay, it's by exploiting multiple processors and multiple cores. So naturally, multiprocessor and multi-core scheduling is really important. Okay, although in this class, we can cover only the basics of a CPU scheduling, so that's why the majority of this chapter is on uniprocessor scheduling. But in the next few slides, we will discuss a little bit about the basic concepts, basic principles of multiprocessor scheduling. Okay, to just give you an idea, what are the requirements of multiprocessor scheduling and what are the general solutions. We won't go into a lot of detail because that's too advanced for this class. Okay, but if you're interested, there's a lot of research papers you can read. Okay, you can ask me. I can give you some pointers. Okay. But at least you understand. You need to understand that multiprocessor, multi-core scheduling are really important today, because that's the trend how we can continue increasing the performance of our computers. Well, naturally, multiprocessor scheduling. So from now, I just say multiprocessor scheduling, okay? Because the difference between multiprocessor scheduling and multi-core scheduling is small. Okay? As at least within the concept of this class, we can consider them similar. Okay? So I just say multiprocessor scheduling, okay? To generally refer to the scheduling of multi-cores and multiprocessors. The scheduling is of course a lot more complex when we have multiple CPUs, okay? And also we are focused on homogeneous multiprocessors. So there are the multiprocessors that you are familiar with, okay? Your laptop or your desktop or even your phone, okay? We call them homogeneous multiprocessors because all the processors, they are the same. Okay? They are built in the same way, they also function the same way. Okay, so that's why they call it homogeneous. But they are also there's another emerging trend in the computing field is that now we are starting to have more and more heterogeneous multiprocessors. Okay, just giving an example, you probably know that the modern Intel processors, they also come in addition to the general purpose processors and the cores of those processors. The Intel processors, they also come with graphic processors built in as part of the CPU, right? And also network processors built in as part of the CPU. Okay, so if you consider the graphic processors and network processors, which are part of the CPU, also as processors, right? They are indeed processors, right? And then we already have heterogeneous processors. Right? We have the general purpose CPU cores, which can run any kind of job. Then we also have a graphic processor, which does graphic processing. We have network processor, which does network processing. Right? So we already have processors. They are on the same die, right? And they are heterogeneous. So then obviously when we do scheduling across these heterogeneous processors, we have to do it. We have to consider their different characteristics. Right? So but that's an advanced topic. Okay? So here we can just focus on the scheduling of the homogeneous multiprocessors. Right? It can be the different cores, different general purpose cores that we have on a processor. It can be the different general purpose processors that we have. Okay, on the same in the same system. Okay? So those are homogeneous, and that's the focus of our discussion here. Alright, so and we also call this type of we mentioned this before too, but we have symmetric multiprocessing and asymmetric multiprocessing. Right? Our focus here is symmetric multiprocessing. So this corresponds to homogeneous processor and heterogeneous processor. Okay, there's a mapping there. Okay, in asymmetric multiprocessing, then each processor deals with different types of jobs. But in symmetric multiprocessing, every processor can service any kind of job. That's the basic idea. Yeah. So, then specifically in the context of symmetric multiprocessing, the scheduling, there are two general approaches to scheduling. One is that we can have all the processes. We can have all the processes share a common ready queue. That's one approach, right? And then this is quite similar to uniprocessor scheduling, because in uniprocessor scheduling we have only one ready queue. Right? There's no reason to have more than one ready queue. Well, unless we want to have different level queues for different schedulers, right? In the multi-level queue scheduling, right? Then in that case we have multiple queues, right? But still, right? But still, all the processes, right? If we consider all the queues as a single virtual queue for that uniprocessor, then we still have only one ready queue. Right? Just within that ready queue, we further have sub queues that are provided for different schedulers. Okay. We can take the same approach for multiprocessor scheduling. We have all the processors share the common ready queue. Okay. And when a processor needs to schedule a process, just pick one from that queue. Right? So another way to implement multiprocessor scheduling you can probably imagine is that we can have every processor with its own private ready queue. Okay. So if I have to draw a diagram, right? So in the common ready queue approach, then what we have is that we have say if these are the processors, okay, and this is ready queue. So we have one queue, and we have multiple processors. Right. Okay. So every processor will just pick the process to be scheduled from the same queue, right. And we can use and again this single queue. For this queue, we can use a single scheduler, say round robin, to dispatch requests to dispatch processes to different processors. Or we can actually use multiple queues. Right? We can convert. Right? We can convert this single queue to actually multiple queues, right? So that we can use different scheduling algorithms, right? Robin or first come first serve. Okay, so you got the idea, right? So, but still, it's a single logical queue that is shared by all the processors. Right, so there's sharing, right? So that will probably make it clear. Right? So all the processes, they will share the queue or queues. Okay, no matter whether it's implemented a single ready queue or multiple level queues, right? All the processes will share the queues. Okay? Now, in the second approach, okay, then what we do is that. So again, we have the we have the processors. Okay, we have the queue. We have the processors P0, P1, PA. Okay, each one have its own queue. Okay. So we have Q0, Q1, Qm. Okay. So when a processor needs to schedule a process, say P0 needs to schedule a process, you just pick a process from Q0. Okay. So which processor a process will be scheduled to is really determined on which queue it is located in. So we will admit processes, right? So the processes are here. When we admit processes, they will be assigned to different queues. And then they will be picked up by the processor that corresponds to the queue that is placed in. Okay? Well, in contrast, and so this is a private queue. Right? This is a private queue approach. In contrast, in the shared queue, global queue approach, right? This is a common queue. Okay, which is also called global queue. Okay, in this approach, come back. Excuse me. In this approach, all the processes, okay, they share the queue. Okay, all the processes they share the queue, right? And when the processes are admitted into the system, right? And the processes are admitted into the system, they will be placed in the same queue. Okay. Well, so now let me ask you, which one do you think is better? Take a moment to think about it. Okay, one is a global queue approach, and the other is a private queue approach. Which one do you think is better? Think about it. Well, I checked how much time I have already used for this lecture. Excuse me. Okay, I'm back. I think I have already done 40 minutes. 40. So okay, so 40 minutes. Okay, 40 minutes of the lecture. So 5 more minutes I'll be done. Okay, because the last lecture I used 5 more minutes. I used 55 minutes in the last lecture. So in this lecture I want to give you 5 minutes back. Okay, so but I hope you have taken the time to think about it. The question I just asked. But just like it's similar to the discussion we had before, right? So remember, message passing and the shared memory, which one's better, right? So we talked about that before. Right? Message passing has high overhead, so we thought shared memory might be better. But then what's the problem with the shared memory? Right, synchronization. Right. So here we have the same problem. We have a synchronization problem. Okay. So if we use the global queue approach, right, this one. If we use the global queue approach, right, then all the processes need to synchronize with one another. Right, when a processor needs to grab a process from the queue, you need to lock the queue so that we don't schedule the same process to more than one processor. Right? And similarly, when we in-queue a process, we also need to lock the queue somehow. Right? So the synchronization overhead involved, okay, in the global queue approach. Okay. Well, in the private queue approach, the one that is diagram that's on the right, we don't have to synchronize across the processes, right? Because once the process is admitted, it is placed in one queue, in one queue, right? And then it will be scheduled by that processor that is in charge of that queue, right? So that's it. There's no synchronization required. So that's an important difference, okay? And depends on whether we can efficiently implement the synchronization. It will determine the efficiency of our scheduler. Okay.